Today, we are going to be looking at differential equations. Since you've already searched this video up, you probably know what a differential equation is. However, just to recap, differential equations are basically equations that relate a function to its derivatives. They're like the gossip of math. They tell you how things change over time. For example, how fast your coffee cools down, or how quickly your motivation disappears during finals week. There are a few key approaches to tackling ordinary differential equations, but today we'll be focusing on integrating factor.
Now, let's talk about integrating factors. These are like the superheroes of differential equations. They swoop in to save the day when equations are inseparable or homogeneous. Here's how it works. First, recognition. Integrating factor problems always follow this standard form, whether you have to manipulate it to make dy over dx a standalone variable, or if the question is given as such. Second, we are going to find the integrating factor through this equation. Note that this is the one place you do not need to plus c. It will come later in the question. Third, we are going to rearrange the equation into d over dx times iy is equal to iq. Fourth, we can integrate as normal since q is a function in terms of x. This allows us to solve for y. It's like turning chaos into order with a single multiplication. Now, let's try to apply this to the following equation. At first glance, it seems like we can use the earlier strategy we talked about, homogeneous equations. After all, on the left-hand side, we can see y over x. However, there is no y on the right-hand side. So, what do we do? Looking at the form, we can see that it fits the standard form of integrating factor, where 3 over x times y is a function of x multiplied by y, and sine x over x cubed is a function of x. Let's return to the steps from just now. By comparing our question to the standard form of an integrating factor question, we can see that px is equal to 3 over x, and qx is equal to sine x over x cubed. This verifies that we should use integrating factor to solve this problem. Going back to our 4 steps, this means that we now need to find the integrating factor. We can find the integrating factor through the equation I equals e to the power of the integral of px. Since we know that px is equal to 3 over x, we can plug this into the equation, giving us I equals to 3 to the integral of 3 over x. By using our integrating skills, we can find that the integral of px is equal to 3 ln absolute value x. Since e to the power of a natural log can cancel out, we can then reduce this further to find that our integrating factor is equal to x cubed. Next, since we have our integrating factor, we can then rearrange our equation into a form that makes it easier to integrate. By using the formula above, we can rewrite the question into d over dx times x cubed y is equal to x cubed times sine x over x cubed. This can then simplify into d over dx times x cubed y is equal to sine x, which is an easier function to integrate than our original question. Last, we can solve for y by integrating the right-hand side. This gives us x cubed y is equal to the integral of sine x. Using standard integrals, this means that x cubed y is equal to negative cosine x plus c. Always remember to plus c, otherwise your final answer will be incorrect. Since we want to solve for y, we can do this by dividing both sides by x cubed to isolate y, resulting in our answer, negative cosine x plus c divided by x cubed. By using the same 4 steps, this allows us to solve any integrating factor problems. So, why do we even care about this? Other than the fact that you may need to learn this quickly for whichever looming math test, differential equations are also always hidden in plain sight. They describe how rockets launch, how pendulums swing, and even how populations grow. So, the next time your coffee gets cold, blame math, not your friends.